Hi, I'm Nanette Hernandez, and I'll be talking about the workshop Learning Form from the Merge Surface Extraction example. So our objective is to create a surface halfway through the thickness of the solid walls, and then mesh the surface with a 2D plate element. Create the remaining of the plate element model and analyze the model and display the results. So the problem would be to determine the model display the greatest amount by displaying the different shape. Then the material will be selected. It would be aluminum, and then we would load the edges of the holes. These are some key concepts and steps that we will be doing from the database geometry elements, loads, materials, properties, analysis, and results. So for the first step, we'll create the new database and import the Parasolid file. So first, we will click on the file and then on new. And then we would be entering the mid surface as a file name right here. Then we click OK. And to set the tolerances to the base of the model, we'll have to select this and set the analysis code to Nastran, and then click OK. Then we'll click File and import to import the Parasolid, and then select the G box and click Apply. Then click OK to the summary when the summary import appears, and then click the ISO 3 view icon. This is the junction box should look like when observing it in the ISO 3 view. For step 2, create a group of mid surfaces, and you'll be clicking on group, create, then enter the mid surfaces from a new group name right here, then select the make current, then click apply, then cancel. For step 3, we'll be creating the mid surfaces from Parasolid Solid, and we'll be clicking on geometry, and in action we'll be selecting create, and in object surface, and in method miss surface. We'll have to click on the automatic icon and enter the following number onto max thickness. And in for the solid list, we'll be selecting the solid, and you should click apply if the auto execute is checked. Do not click on the apply button. On step 4, the post miss surfaces group only, we'll be clicking on group, then on post, then select the miss surfaces from select groups to post. That would be here, and then you select apply, then cancel. On step 5, the edit gusets, we'll be selecting geometry, then in action would be edit, object, surface, method, trim, and would check the delete silver surface that we have to be selected, and to select a surface to trim, click on any of the gusets. So this would be the gusset. To select the trimming edge, click on the sloped edge of the gusset, this one. And then repeat the procedure for the 7 remaining gussets. For the step 6, associate gusset edge to mid surfaces. So to associate the gusset edges to the junction box surfaces, we need to associate the gussets to the junction box to make the quad meshes congruent during the paver meshing. So we'll select geometry, then in action we select associate in an object curve and a method surface. And then we'll be selecting the gusset edge on the vertical edge in the curve list. And then in the surface list, we'll be selecting the surface 1, which will be this. And then we'll click apply, then repeat for all the remaining gusset edges. On step 6, associate the gusset edge to mid surfaces. So here is the model after all the gusset edge has been associated to the junction box mid surfaces. The associated edges are indicated by the triangles. On step 7, paver match all mid surfaces. And we'll be paver match all mid surfaces of a solid. So we'll be clicking on the elements, and there will be on action. We'll click on create object, select match, and type surface. So to make sure the quad, the paver, and the quad 4 are selected, we'll be selecting it here on the element shape, quad measure, paver, and topology on quad 4. So on C, we'll be removing check for the automatic calculation and enter the following number for the edge global edge length. So we're clicking on surface list, select all the surfaces by dragging a box around the entire object, and then click apply. On step 8, equivalence nodes to connect to the quad elements. So observe that none of the elements or geometric boundaries are connected. They have free edges. This problem will be remedied with the equivalence command. So we'll select elements again, and we'll change the option to verify object to element and test to boundaries. Then we'll be selecting free edges on display type, and then click apply. On step 8, the equivalence nodes to connect to the quad elements will select element, and the action would be equivalence, the object will be all, and the method would be tolerance cube. Then we'll click apply, and then we'll select elements again and click on action to verify object to element and test to boundaries. Then on display type we'll click free edges, and then we'll click apply again. For step 9, we'll be creating a total load at the edge of the selected holes of the model. So we'll be clicking on loads, and in action we have create an object, total load, and in type element uniform. Then we'll in new set name will have a total dash load, and in target element type will have 2D. Then we'll click the input data and enter the following coordinates, and then click OK. For step 9, we'll create a total load count and constraints. So we'll be clicking on the selected application region right here, and then click on edge icon. That would be this one, and then click the edge of any small holes on the end of the junction box at the greatest y coordinates. This one. Click add to each of them and repeat C and for the remaining 3 holes. Click OK, then apply. On step 9, create a total load. This is all in illustration of the junction box mid surface is matched with a total load. On step 10, constrain the base of the junction box. So bolt down the base of the junction box, constrain the 4 holes at the bottom so that they are fixed. So we're clicking on load, then we'll have the action to create the object in displacement and the type in nodal. Then we'll enter fixed on the new set name, and then click input data. Then we'll be entering this following coordinates on translation and in rotation. And then we'll click OK. Then we'll select the application region, and then we'll select the curve or edge icon, and we'll select the edge of any holes on the base and click add. And then we'll click OK, and then we'll click apply. For step 10, constrain the base of the junction box. This is what the object should look like when the constraints are applied. You can observe that the constraints on the bottom of for the 4 holes of the junction box are all in 6 degrees of freedom. Step 11, add materials and element properties. Add the material properties for the model. And in materials, you select materials, and then in action, you select create an object isotopic and a method manual input. Then you will be entering the material name would be aluminum, and then click on the input properties. And in the input properties, you will type the following number in the elastic modulus and the following number in Poisson radio. Then click OK, then click apply. On step 11, add the material and element properties. Add the element properties, and you click on properties, you create, in action you click create an object 2D and in type shell. Then you enter the 2D dash shell on property set name. Make sure that it is homogeneous and standard formulation. And then click input properties, and then click input properties and click on the match prop name icon, this one, and select aluminum. Then enter the following number in thickness and then click OK. Under the selected member, select the entire object by dragging a box around the junction box. Then click add, and then click apply. On step 12, check the load case. So to check the load case, we'll go to load cases. Then in action, we'll select modify. Then we'll select the load case name defaults from existing load base, this one, and then check to see the total load and the constraints are assigned to the default load case. Then we click cancel. On step 13, return the analysis. Run the analysis of the model. So we click on analysis, and in action we have analysis, an object, entire model, and method will run. Then we'll click on translation parameters right here. Then we'll be clicking on the select XDB and in print right here. Then we click OK. And then we'll click on subcases right here and make sure the default subcases is selected right here. And then click apply and cancel. Click on subcase selected. Select. Make sure that the subcase default is selected and click OK. And then click apply. On step 14, look for the results. So observe the results generated by the MSC master. Analyze the access results and an object attack XDB and in method result entities. Then would be selecting the results file, selecting the mid services XDB, clicking OK, then apply. On step 14, look for the results too. Look at the deformation created by the load. So we'll be clicking on results, then on action create an object deformation, and we'll be selecting on select results the default A1 static subcase, and we'll be selecting on selected deformation results the displacement traditional, and then click apply. So we'll be removing the undeformed plot and erase the geometry to get a better illustration of the load effects. So click on the display attributes over here, icon, and then remove the check from the show undeformed box and from the show tile box as well. So there's two. Then click apply, and then click plot erase icon, this one, and then click erase under geometry, and then click OK. Step 14, this is how it should look. And then we would be looking at the Von Mises stress for the junction box surface model. So in results, we'll have an action create and an option fringe. We'll select the result case on the default static surface. And in the select and fringe result, we'll select the stress tensor, and then we'll click apply. Then we'll modify the attributes to get a better fringe plot. So we'll be clicking on the display attributes icon, change the display to element edge, then uncheck the show file, the show title, and then click apply. This is the final illustration shows the fringe plot along with the deformation plot. And this is the end of the video for the workshop number 4. Thank you for watching.